Okay, hello everybody. This is the video that I'm promising you. Hello everyone. This is the video that I promised you, titled "What are generating functions actually?" Or maybe I could have titled it "What is the point of generating functions?" Like, why did we bother introducing formal power series to describe sequences when we could just use the sequences themselves? What's the benefit to it? Like, these are reasonable questions, and you deserve an answer that's better than, well, because I said so. So let's get on with it and try and answer these questions. So just to make sure that we're all on the same page, an exponential generating function is a formal power series of this particular form here. We sum over an x to the n over n factorial. And when we say formal power series, what we mean is that we're not really going to care whether or not this series converges. It's not that convergence isn't an important topic, it is an important topic, but we're going to kind of ignore it because it's not going to really be that relevant for how we're going to use series. And so these an is what represents our a objects of a size n, whether we're talking about derangements or partitions or involutions or whatever. And at least one point that we could argue right now is that for a generating function, we want to wrap up all our knowledge of one sequence into, whether it's partitions or whatever, into one entity that we can manipulate, this function here, rather than thinking about it as a sequence. We'll just think about it as one function. We think of functions as one thing. But I mean, this raises an important question. Why use polynomials? Or, well, series are just infinite polynomials, right? What does this buy us? Well, the first thing I would say is there's a potentially useful analogy between thinking about what would happen if you used a set of size n rather than the number n. So, like, this would contain more information. We have the elements of the set that is getting carried around, not just the size of it. And when we're performing operations on that set, we can exploit the fact that we have this knowledge of the elements. And when we're thinking about generating functions, we're thinking about something similar to this analogy here. Unlike sequences, polynomials have natural algebraic objects on them, like adding, multiplying, differentiating. I mean, in principle, we can define all of these things for sequences, but that's a little bit artificial, whereas with polynomials, we do these things already. And this isn't going to be meaningless symbol shuffling. Like, these operations that we're going to do to generate functions are going to correspond to natural combinatorial operations on the underlying objects that we care about. And in this talk, I'm going to talk about 4: addition, multiplication, differentiation, and composition of power series. There are more, but like, these are the most important ones here. But first, we should give us a few example objects of things that they're gonna carry around. So we've all seen permutations. A permutation is a bijection from the set 1 through n, and we know that there are n factorial such permutations, and that this is the exponential generating function that we should be getting. The next thing that I'm going to use for my examples are partitions. And we've all seen partitions already. We're very familiar with them. What's a partition? It's a set of subsets that we call parts of 1 through n, and we want the parts to be disjoint, non-empty, and we want everything to belong to some part. And although I have written down this exponential generating function for you in the tutorials, like, you might not have proved it, you might not understand quite where we get that one yet. You will by the end of this, like, mini lecture. And the final example I'm going to make use of is this notion of what I would call a binary tree. So what do I mean by this? Well, we'll talk a lot more about trees when we get to the graph theory part of the course, but the definition here is reasonably simple. A binary tree is either a leaf, quote unquote, or it's a branch, quote unquote, consisting of, well, in this case, a number and a pair of binary trees. If this definition sounds circular, it isn't. As long as we only build bigger trees out of smaller trees, right? But you're probably, unless you've done a lot of computing, that might seem like, well, okay, what are we actually talking about here? So here are some examples of binary trees of size 3. So in this case, what I'm meaning by the size is all of these red nodes that I've labeled with some number. And the black ones would be the leaves. So the size in this case that we care about is the number of internal nodes. And these are in fact all of the binary trees of size 3, at least up to relabeling. Like if I move these labels around, I'm going to refer to these numbers 1 through 3 or 1 through n as labels. And so I guess in total that there would really be 3 factorial times 5, so 6. So 6 times 5 is 30 binary trees of size 3. But here are the main 5, I guess. And I should give you their generating function, right? So this is a exponential generating function for the binary trees. I'm not going to prove that this is the generating function. You can Google for a proof if you're desperate to see one. I'm mostly introducing these binary trees so that we can get nicer pictures, right? And also because it's kind of criminal to go through a combinatorics class and not mention the Catalan numbers. And the Catalan numbers are these things at the bottom. This 2n choose n over n plus 1. And we use this for counting binary trees. So we've got these 3 examples in hand, and so now we can talk about the operations that we can do with generating functions and what they mean for our objects. So addition is kind of like the simplest thing we could do with series, right? So we've got 2 series, s of x. I didn't mention this, but I'm using s for permutations. S in this case would stand for symmetric. It's not really important that you understand why, but if you're interested, that's why it's an S. And so we're saying, well, what sequence does this new generating function that we get represent? So we could do the calculation. It's a pretty easy calculation to do. We do what we do with polynomials. We collect the coefficients for a given power of x, and then we can see that the nth coefficient of s plus par is s sub n plus p sub n, where those are the number of permutations and partitions on n labels respectively. And so our natural question is, well, what does this count? Like, if I'm saying that we're using generating functions to represent sequences of things that we can count, then what does this represent? And, well, if you think back to just operations on sets, what is the operation on 2 sets that when you do it, you get the size to be the size of the sum of the sizes of the 2 constituent sets? And that's the disjoint union. So the union of 2 sets that don't overlap, as opposed to, say, if I take the union of 1 through n and if I take the union of the set 1, 2, 3 and the set 1, 2, 4, well, I'm only going to get the set 1, 2, 3, 4 because things are getting repeated. And we throw away the repeats. But when we think about the disjoint union, then just because both sets had a 2, we're still going to try and remember that they came from different sets. So that'll make a bit more sense in a second. So what we're counting here are what I would call an s plus par object of size n. So each s plus par object is either like this thing on the left, this thing here. This is my way of representing a permutation, so an ordered list of numbers 3, 2, 1. Or disjoint union. It can be a partition of the set 1, 2, 3 into into a partition. So it's always either or. But you might be concerned because, well, what if I wanted to add par to par? Do we get par x or do we get 2 par of x? Because if we take the union, we would get the first one. But in this case, because we're taking the disjoint union, as I say, we kind of remember that whether the partition comes from the first set of partitions or the second set of partitions. And the way I like to think of this is just pretend they're different colors. So the ones on the left we could say are blue, the ones on the right we say are red, and so these two are two different structures on the set 1 through 5, because these ones come from the left partitions and these ones come from the right partitions. Okay, so and 2 par x is what we get for our exponential generating function. Addition is pretty easy. Addition is by far the easiest one to think about, because disjoint union is a pretty easy thing to think about. And so the next thing we would want to ask is, well, is there a natural meaning for multiplication? Now, multiplication is kind of the really important operation on generating functions because, and I'll mention this a bit later, it's how we can decide which generating function we should be using in the first place. Should we be using an EGF? And all of my examples for just now are exponential generating functions. Or should we be using an ordinary generating function? And I'll touch on this a bit later. So if we were to multiply the sequences, well, we know the obvious thing to do with sequences would be to multiply each of the elements in turn, right? So I would take the nth element from the first sequence, I would take the nth element from the second sequence, I would multiply them together. Now, that's not the wrong way to define multiplication per se, but it's not the natural way we do it, because when we do it with polynomials, what we do is we have to distribute across and then collect like coefficients. And so if you do this with the power series for permutations and multiply by the power series for partitions, we're going to get this series with where the nth coefficient is this n choose k, sk, p n sub k, and then take the sum over all k. So again, we need to ask the same question. What set of objects has this size? So if we were to fix a particular k, right, then we can say, so we've got 3 things here making like 3 independent choices, and n choose k is like picking k elements from our n set, and then s sub k is the number of permutations on a k set of size k, and p sub n minus k is the number of partitions on a set of size n minus k. And so what we can think of then is we take our n set, our set of n labels, and we split it into 2 groups, the k ones and then the n minus k ones, and then we form a permutation on the k that we picked and a partition on the other n minus k. right? And then we'll sum over them all. So what we're doing here is we're counting the pairs of permutations and partitions. We're counting the number of pairs of permutations and partitions such that the total number of labels that are shared between the two adds up to n. So this is what I just said, and here in the addition case I had two pictures up, whereas for our what we're doing is this is really one structure. A structure is made up of two parts. One part is the permutation part and one part is the partition part. And in this case we've given the labels 1, 3 and 4 to the permutation and the remaining labels 2, 5 and 6 to the partitions, and then our one object is this pair taken together. And so that's what I want you to think about when you're thinking about the product of two structures, like because this is the natural combinatorial way to do it. Share your elements across the two pairs in all the possible ways. Okay, so I want to calculate something now, and we've seen this notion that we call a derangement in the lectures. And here I've written down a permutation, and if you haven't seen this notation before, the top row is our domain and the bottom row is what every element of the domain gets mapped to. So 1 gets mapped to 1, 2 gets mapped to 3, 5 gets mapped to 5, 6 gets mapped to 2. You get the idea. And so if we stare at this permutation, then we can think of this permutation as being built up from an identity function on 1 and 5, because 1 gets mapped to 1 and 5 gets mapped to 5, and the remaining 4 things form a derangement. None of them are getting mapped to themselves. And so this is starting to sound a bit like a product, right? Because in fact any permutation can be decomposed this way into an identity function and a derangement. And so I would need to tell you what the exponential generating function for the notion of an identity function is, and well, there are as many as there are sets. That seems reasonable to believe, and the exponential generating function for sets is e to the x. And for derangements we have this exponential generating function. We're just going to call it derx because we don't know what it is yet. And s of x is our exponential generating function for our permutations. And so thinking about this permutations as this product, we have an equality. S of x is equal to e to the power of x times the number of the der of x. And if you just rearrange that and substitute in what we know to be the exponential generating function for x of x, this gives us an exponential generating function for the derangements. And if you were to look at the nth coefficient of this generating function, you'll see that this is the formula that we get, and this formula just comes straight from doing the product. And this is the correct one, and so that's good. This sort of gives us an idea of one way that we could use exponential generating functions or generating functions in general to work out the values of a sequence that we don't know by figuring out how it relates to other sequences that we do know. That's all I'm going to say about multiplication, I think. As long as you remember this picture, or like this idea of splitting up between two, that's the main thing I need you to take away from this, because we're going to come back to it in a bit. Okay, so that's addition and multiplication down. What about differentiation? Because differentiation is a natural thing to do with power series, and we can define it completely formally. And instead of using permutations or partitions, this time I'm going to use binary trees for my examples, because it's going to give us a slightly nicer picture, I think. So we can do the calculation. So include the power series, do the term by term differentiation, simplify it a little bit, and then we look at this and we go, huh, that's kind of weird, because the nth coefficient of this power series is b sub n plus 1, which is the nth plus 1th coefficient for the exponential generating function for binary trees. So somehow, even though we think we're going to think of an n element of this set as having only n labels, it also needs to kind of have n plus 1 labels. So how are we going to do that? I guess we'll just have to make an element up, and we'll not worry too much about how you can always do this. You can in fact always do this, but things are going to get a bit more concrete with a picture. So I've used blue to in here to show that there's, so between the blue and the red you can see that there would be 4 internal nodes, but I've only labeled 3 of them, and I've kept this blue ones out separate. And so when we ask you like what a derivative of a binary tree of size 3 is, well, it's going to be a binary tree of size 4, but we've got this special blue labels that are not like the other labels because they don't have a number. They're not real labels. They're these fake dummy labels. But this is weird, right? We've went from like having like these 3 labels which were concrete and these measured things that we cared about, the internal nodes of a binary tree, and then we've just sort of said, well, if you take the derivative, you need to look at 4 because they somehow have this like hole in them. Maybe this seems a little artificial, but I can assure you that this is useful stuff. But before I do that, I want to talk about taking multiplication and differentiating and doing it together in one operation. So this is the operation that I would call pointing. And so if I have some exponential generating function a, I'm going to define this by saying take the derivative of a and then multiply it by x. And you power through the notation, you'll see that what this gives you is the sequence n times a to the n of x to the n divided by n factorial, sum over all n. And we need to ask the same question. Well, what are we counting now? What does n times a sub n count? Well, this doesn't seem too bad, right? It's the a structures of size n, but we also have this additional choice to make from n, and so we can think of that as marking out one of the labels as special. So here's a picture. So this is what happens if we point a binary tree of size 3. I have labeled it's 3 in all of these examples. It needn't be 3, but I've marked them all with a pentagon to show that they're special. And this notion, this rooting, this is a useful thing to do. And in fact, we've already seen an example where we might do this, because what it lets us do is it lets us take a like quote unquote symmetric structure like a tree and then break it up, like break the symmetry by designating some part of it as special. And this is often a good technique for counting things. And in tutorial 3 question 7 we asked you to prove a particular identity. I noticed that there's a mistake here. The upper bound should only be up to n rather than 2 to the n minus 1. That was silly. But we asked you to prove this, and we said we wanted you to do it by differentiating the binomial theorem. And I don't doubt that most of you thought, why on earth is differentiating the binomial theorem the right thing to do? Well, now you can sort of prove it combinatorially. We've got this equation, the sum of n choose k is equal to 2 to the n, and that's all the ways of picking subsets. And when we point it, what we're doing is, if you like, picking a team and then choosing its captain. We've picked a special one out of it. And if you look at the top equation, that's what we're doing. So we often do this because it's like a symmetry breaking thing, and it marks things out as special. And I think that's all I have to say about differentiating. I do think this pointing is perhaps a more natural thing to understand than doing the differentiation itself. So I should move on and talk about composition. Now, I don't think we've really mentioned composition to you in the lectures, but these power series are in principle functions, and we can always compose, and we like to compose functions and build up more complicated things that way. Like if I give you a function f and a function g, then it's plausible that you might calculate f of g of x. And that's kind of what I'm suggesting we do here. This operation is a lot more complicated than the last three. And it isn't defined for all power series, but I'm going to ignore that, and you can check Wilf for the details if you really care about it. So if we substitute this s of x into the power series for the binary trees, this is as far as I'm going to go with simplifying the formula, which isn't very far itself. But we can ask, what does the nth coefficient of this count, just like we've been asking before. And so you need to stare at this and say, like, where is the x to the n coming from? And since we've got a product here, what you realize is that, well, since we're doing this silly sum with the s of x to the n, we can always get a product of an s by itself, or an s times an s, or an s times an s times an s. And with this, we'll need to distribute all the labels between every element in our tuple. So what we're doing is, for any k tuple of, in this case, permutations, as long as these k permutations, the total number of labels adds up to n. But we also have to have a binary tree of size k, which is this b sub n thing. So what we're doing is, effectively, we need to partition the number n into all possible partitions into non-negative integers, and then for each partition we have a particular coefficient, and we're summing over all of these. And you can Google this formula if you actually care about it. But I'm not interested in giving you a formula. I want to give you a picture instead, because like, that was scary, right? And I don't want you to panic. So if you believe me, there's another mistake. So these are B compose S, or structures of, that should say size 9. I don't know why it says size 3. And so if we just look at this left one, what I've got are three permutations. There is a gap between the permutation 5, 6, 7 and the permutation 8, 9. And we've got a binary tree sort of hiding behind it. And similarly on the right, we've got 5 permutations, and they share all of the labels 1 through 9 between them. And then we've made a binary tree out of this. So what we're doing, if you like, is we're creating this sort of 2-level structure, binary trees of permutations. And the size n, in this case, the n labels are all labels of the permutations, because if you like, the labels for the binary tree are the permutations themselves. Now, you might be able to see why this is useful, because because the way we build complicated structures in principle, right, is that we like to split them up into simpler pieces and then combine them together. And complicated objects often have multiple levels of structures, like what we see here, where we have a binary tree of permutations. So I'm going to give you some examples of where this would be useful. So I've already mentioned that the exponential generating function for sets is e to the x, and if you figure out what the exponential generating function for non-empty sets is, it'll be ex to the minus 1, because there's only one set that is empty. And what I want to do is talk about this formula for partitions that I mentioned at the beginning. So a partition is a set of non-empty sets. We have this two-level structure. We have the top level structure, which is a set, and inside of each, in the lower level structure, is the idea of a non-empty set. So we can just take the composition, and that's what we're doing here, and then we can just plug that in to get our exponential generating function being e to the x minus 1, which is what I claimed at the beginning. Maybe if you've been paying attention, you might realize that this particular example is kind of cheating, because if we go back to here, the partitioning is already kind of happening in how we defined composition of structures. So I should give you another example that isn't quite cheating, and one that you haven't seen. So in a ranked choice voting system, which the UK, for ridiculous reasons, does not have, if you go into your ballot, you'll be asked to rank all of your candidates in a particular order. And for us, we're going to allow you to rank some things to be the same. So here is one such ballot, from which you can infer that I am one of those academic leftist types, where we would say that the set containing only the Green Party is the best choice, and then maybe the set containing only the SNP is the best choice, and maybe I don't care whether or not the Labour Party or the monster raving loony party get in if it reached that far, and similarly maybe I don't care if it's Conservative or UKIP. And so I've got these sets that represent I don't have a strong preference either way, whereas between, say, the Green Party and the SNP, I do have a strong preference. Other political affiliations are available. But what we have here is an ordered list, which is another way of saying permutation, but I don't want you to think of permutations and ordered lists as the same thing, because they do have the same exponential generating function, which we can see here, but they have different ordinary generating functions. I'm not gonna say more about that. But so what we have here is an ordered list of non-empty sets. So we do the composition, and our exponential generating function for these ballots is L compose E plus, which is going to give us this exponential generating function 1 over 2 minus e to the x. And so before we leave this topic, I'm going to give you two exercises. I didn't bother to write them down, but I do have two exercises for you. So take the example from this week of an involution. Can you figure out a way to express that as a composition and then work out its exponential generating function? I mean, I already would have shown you the exponential generating function in the tutorial, but try and do it just by thinking really hard and then writing down the answer, rather than using the recurrence relation to work out what the exponential generating function would be. And a second exercise, if you're filling up for it, is see if you can understand the chain rule from calculus combinatorially. Now you're going to need to use both the composition and derivative constructions that we've talked about on power series, but if you can figure out either one of these, send me an email. I'd love to hear if anyone actually did this. Okay, so I've talked about 4 operations which are very nice in that we can do stuff, but you're probably thinking, well, I haven't really talked about the inverse operations. Like, I haven't talked about subtraction, I haven't talked about division, I haven't talked about integration. And that's because they're not as nice. Like, what is the combinatorial meaning of minus a of x? Or 1 over 1, or 1 over a of x? There are ways to make sense of these. I've linked a paper, lobes, sets with negative numbers of elements. But these things aren't very natural, like combinatorially. And so in this case, it's often easier to think of this in terms of solving equations, just like you did way back when you were probably learning about subtraction and division. So don't think about a is equal to b minus c. Think a plus c is equal to b. Don't think that a is equal to b divided by c. Think a times c is equal to b. And like you can see that I already did this sort of cheat earlier on in the talk when I was talking about derangements, right? Because I said that a permutation is a product of a derangement and a set. And so maybe what I should have said is a derangement is a permutation divided by a set. And there are ways to make sense of this, but we're not going to talk about it. Integration, on the other hand, is a bit weird. You can kind of think of it in this sort of solving equations way. Like integration of power series is easy, just integrate term by term. But if we go back to the pictures, like when we differentiated, we added in a dummy label. And so if we were integrating, we would need to remove the dummy label. But how do we know which one's the dummy? If your label sets are ordered, this makes sense. You just say either like, okay, I add a dummy label, I'll make it the biggest one. And then when you're integrating, you take away the biggest one. But I'm not going to talk more about this. Just think about solving equations for these 3. It's not so bad. Okay. What about ordinary generating functions? I've only talked about exponential generating functions because, well, weirdly enough, they're kind of the more basic one, although they look more complicated. So, but what about ordinary generating functions? When do we use them? After all, like this was the first thing we taught you about. So most of what I said works pretty similarly for ordinary generating functions, but I do need to talk a little bit about multiplication. So we're going to compare how multiplication works for the ordinary generating functions, that's this first equation, with how it works for exponential generating functions. This is this bottom equation here. And you can see that they kind of look the same, except that the exponential generating functions has this n choose k term. And if you recall, like what the n choose k was doing was, that was our number of ways of choosing labels so that I could give k labels to a. I realize I've written a sub n, whereas when I was supposed to write a sub k. C'est la vie. So I needed a way to split the labels, but I can't. I'm not doing that here. Like that n choose k has been replaced by a 1. And so this is where I like say that we use ordinary generating functions to count different things than exponential generating functions. Exponential generating functions we use for counting these labeled things, whereas ordinary generating functions we can't use for counting like what I would call an unlabeled thing. Because when you have an unlabeled thing, the only way to split up the labels, so to speak, is by the number of them there is, which is unique. If you say I'm going to split it into a set of size 3 and a set of size 5, there's only one way to do this when we're not caring about the labels. And so, what do I mean when I say an unlabeled structure? Well, here are some binary trees of size 5, and on the left I have a labeled one. That is, I've marked all the nodes with a number 1, 2, 3, 4, and a 5. Whereas on the right, I've left them all blank. If you like, I've forgotten what the labels were. And so because for labeled ones, we have all these additional choices to make about where to put the labels. That's where the divided by n factorial is coming from. But for ordinary generating functions, that's for counting things like this thing on the right, where we only really care about the shape. And you can see that the thing on the right is, in some sense, more symmetrical, because the thing on the right is more symmetrical, because the thing on the left, well, for the thing on the right, it doesn't matter whether or not the thing at the top is a 1 or a 5 or a 3. I can just shuffle them around and it doesn't matter. Whereas for the ones on the left, the labeled trees, this does matter. The trees with a 1 at the top are very different from trees with 3s at the top. Whereas that distinction goes away when we think about unlabeled structures. So yeah, that's just what I said. For ordinary generating functions, we use it when talking about unlabeled structures instead. Before I move on, what I do want to say is that these sorts of unlabeled structures, although they're in some sense simpler and there's less of them, they're usually a lot harder to count. It's pretty easy, for example, to prove that there are n to the n minus 2 labeled trees on n labels. Whereas if I were to, I don't actually know of a simple formula for the trees, for unlabeled trees of size n, at least not off the top of my head. And if we're being clever, the way we define an unlabeled structure is as the classes of labeled structures which are the same up to relabeling. I don't know how helpful that is to say, but I'm trying to avoid using the word group action. There are other kinds of generating function. I'm not going to say pretty much anything about them. You can look at Wikipedia for a list. There's Dirichlet generating functions. These are like zeta functions. These are quite useful in number theory. You get probability generating functions, where the coefficient is the probability that a random variable is equal to n. This assumes that the random variable has natural values. There's bivariate generating functions. There's so many of them. Laurent series, Bell series, etc. You can look them up, but the important thing is how to interpret multiplication. Multiplication for Dirichlet series is interesting because because you're summing over divisors. For probability ones, that's like making independent choices from a random variable. And yeah, the main thing is how does multiplication work, and that determines which generating function you should be using in an application. But EGFs and OGFs are the most important ones, at least in my opinion. So you might suspect that since I've been talking about all these like combinatorial objects, and maybe there was just some way to define these sequences of combinatorial objects in a way that we could define these notions directly on the objects, the sequences of objects, and then wave a magic wand and spit out the generating function. And we can do that. I'm not going to explain what this definition means, but this is something that I care a lot about. You've got a notion of a combinatorial species. It's a functor from the category of finite sets and bijections to itself. You can Google what all those words mean, but you don't really need to worry about it. Basically, these things are rules for turning sets of labels into sets of objects, like trees, partitions, permutations. And it needs to satisfy a relabeling condition where the number of objects that we get out only really depends on the number of labels, not the specific label set you use. And these things are, you can think of as a sequence of group actions. So yeah, in conclusion, generating functions are not a symbol shuffling game. The operations that we would do on them correspond to natural operations on the underlying sets of objects. And I hope I've demonstrated that at least a little bit. Different kinds of generating function are used for counting different things. OGS for unlabeled objects, EGS for labeled objects. And if you don't know which to use, think about how the multiplication works. So that's pretty much everything I'm going to say. Hopefully you now agree that generating functions are not artificial or a waste of time. Here are some resources. Generating functionology is pretty good. It's got a lot of tricks on how you can deal with generating functions. This paper, Species and Functors and Types, oh my, is really for those of you who are into programming, particularly functional programming. This was where I learned about combinatorial species. There's this book, I own all of these books. An Introduction to the Analysis of Algorithms by Sedgwick and Flageolet. That's a really good book for that you can follow through, and it really gets you to have a good understanding of generating functions and combinatorial classes and how they work. And the other thing is just the standard reference on combinatorial species by Bergeron, Lebel, and Leroux. If you're feeling brave, you can email me. You can email me and ask to see my fourth year project. I don't particularly recommend that, but hopefully you found this useful, or maybe even a little bit interesting, because I can literally talk about this stuff for hours. I could tell you about how the principle of inclusion and exclusion works for species / generating functions. I can tell you about the implicit species theorem and how you define these sequences implicitly. Like this thing I said for binary trees at the beginning, that a binary tree is either a leaf or it's a branch consisting of two binary trees. I can turn that into a description from which I can generate the generating function directly. And I didn't talk about convergence at all in this talk. Convergence is very, very important. But I kind of need to end the talk somewhere, and I've ended it here. And thank you for listening, and hopefully this was interesting.